Hello guys, welcome back to my YouTube channel. In this video we are discussing about the subject the mathematics for CSE stream. The topic is Taylor series expansion. The introduction is the Taylor series are named after Brooke Taylor who introduced them in 1715. A Taylor series is also known as Maclaurin series when zero is the point where the derivatives are considered after Colin Maclaurin and who made extensive use of this special case of Taylor series in the mid-18th century. Taylor series is also known as an expansion of a function it into a infinite series or a variable x or into a infinite series plus a remainder term 1. The coefficients of the expansion of the subsequent terms of the series involve the successive derivatives and of the function. The function to be expanded should have an nth derivative in the interval of expansion. The series resulting from the Taylor's expansion is referred to as the Taylor series. Taylor series is infinite and the only concern is the magnitude of the remainder. Given the interval of expansion a phi and the phi b, the Lagrangian form of the remainder is given as follows. It is known as the introduction of Taylor series. Let's move on to the concepts. The concepts are the applications of series, the applications of Taylor series, the techniques of a Taylor series, advantages of Taylor series, and the limitations of Taylor series, the formula, exception principle of Taylor series, and the working principle of Taylor series. Let's move on to the first topic. First topic is the applications of Taylor series. The applications it is helps to find the sum of the series and to evaluate limits, and it is used to approximate polynomial functions, and it is used for estimating the value of a function at each point if the functional values and derivatives are identified at a single point. Probably the most important application of Taylor series is to use their partial sums to approximate functions. The techniques of Taylor series, the Taylor polynomials can be generated for a given function through a certain linear combination of its derivatives. The idea is that we can approximate a function by a polynomial, at least locally. In calculus we discussed the tangent line approximation to be a function. We found that the linearization of a function gives a good approximation for points close to the point of tangency. If we calculate second derivatives, we can similarly find a quadratic approximation for the section for the function. Third derivatives go to the finding a cubic approximation about some point. I should emphasize from the outset that a Taylor polynomial is a polynomial. It will not be able to exactly represent a function which is not a polynomial. In order to exactly represent an analytic function, we will need to take infinitely many terms. We will need a power series. The the Taylor series techniques are the Taylor series for a function is formed in the same way as a Taylor polynomial, and the difference is that we never stop adding terms. The Taylor series is formed from an infinite sum of the function's derivatives evaluated at the series center, and there is a function derivatives evaluated at the center, and there is a subtitle issue here, and it is possible to find a series representation for given function. Not always, however, when it is possible, we can call the function analytic. Many functions that arise in applications are analytic. Often functions are analytic on subdomains for their entire domain. We need to find different series representations on opposite sides of a vertical asymptote, and what we learned in the last chapter still holds. There is an interval of convergence. The series cannot be convergent on some disconnected domain. but for a given function we could find a Taylor series for each of the domain and ignoring certain pathological maths examples. And the next topic is the advantages of Taylor series. The advantages are that it is very useful for derivations to derive the problems or mathematical integrated problems, and it can be used to get theoretical error bounds, and power series can be inverted to yield the inverse function. It is the only way for computers to even solve equations. The next topic, the limitations. The limitations are also known as disadvantages. The successive terms get very complex and hard to derive, and the transition error tends to grow rapidly away from expansion point, almost always not as efficient as curve fitting or direct approximation. And the next is the formula of Taylor series. The psi n is equals to 0 to infinity f power n of a divided by n factorial of x minus a power n whole power n. The n factorial is represents the factorial of n, and the a represents a real or complex number, and the f power n of a is represents the nth derivative of f evaluated at the point a. And the next topic is the exception principle of the Taylor series. It is the principle of Taylor series that this principle dictates that any non-recurring or unusual nature should be reported to the senior managers. It helps the tier executives and the top managers to make decisions. Management by exception helps managers step in when the company's employees have failed to meet the organization's standard performance. And it is the working principle of Taylor series. Working principle of Taylor series in mathematics. The Taylor series or Taylor expansion of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. For most common functions, the function and the sum of its Taylor series are equal near this point. And thank you guys for watching my